All right. Now, we left off here. We were talking just about simple linear regression, and we weren't doing any inference. We were just doing descriptive statistics. And we said, okay, here's the formula for the slope of the regression line, r times sdy over sdx. And some people after class asked me, well, what is r, and how do you calculate it? So I just want to show you in the back of the book, because you've all had some form of stats before, and so I want to show you the formula, and it will probably look familiar to you. So if you go to page 151, right here, no, where is that? Yeah, here it is. 151, right here. This is the correlation coefficient in the population, and this is, we use Greek letters, so that's a rho, and our sample correlation coefficient is an r, and basically what it is the product of zx times zy. So once you convert all, like let's say you had a scatter plot with 10 points. So you take the 10 x's, for each x you subtract off the average and divide by the standard deviation of the x's to norm, and they do the same for the y's. And that gives you a standard measuring stick so that there's no units. These are standard units. So then you look at the products. For each of those 10 points, you would take the product of your z-score for the x times the z-score for the y. That's what this is. You multiply those together, and then you add them up and take their average. Divide by n. So it's the average of the products of the z-scores. So basically, any questions on that? There's lots of different formulas for it. A lot of people were asking how it relates to covariance after class. Well, it's the standardized, the normalized covariance. You divide by, it's the covariance divided by the standard deviations of x and y. So that's why r has no units, and it goes between -1 and 1. 0 means no correlation between x and y, no, and -1 and 1 means a perfect correlation, either negatively correlated or positively correlated. All right. Now, so that's the first thing we talked about last time. And then we said, okay, so we said this typical error around the regression line, SD, the standard deviation of the errors. Whoa, sorry. When I do that, you guys tell me. This goes on the video. It looks like I'm insane. Oh, yeah, look at this formula right here, this blank, And then I watch it later and I say, insane. All right, so when I'm talking about this formula right here, that I said I would give you on your exams, the standard deviation of the error is the square root of 1 minus that correlation coefficient squared times the standard deviation of the y's. So that will be given, at least on exam 1. Okay, it's also known as the square root of the mean square errors. So what it is it's the standard deviation of the errors, right? So what do I even mean? So we had an example, I think it was exams versus finals, but we had some kind of scatter plot, okay? And then you get this regression line. Now let's imagine that there was a perfect correlation between the exams and the final. Well, then all the points would lie on the regression line, and you'd have no error. The error means how far off you are in the y direction. This is y, and this is x. The y errors from their predictions. That's what we're trying to get a measure of, the spread around the regression. Well, there's no spread here, and that's a perfect correlation. So, but when there's a spread here, like this, like this points below and so forth, then what this standard deviation of the errors is doing is giving us just a typical measure of our errors, our prediction errors. That's all that's doing, all right? And so so the next line was what? I'm not sure how much we talked about this, but I know in other courses it's talked about a whole lot, in most intro stats courses, that as this r squared, this capital R, this is a specific case of this capital R squared. They're the same when you have 1x. We're going to move into more x's, and then we're going to, this is sort of the general correlation coefficient squared. Okay, so that is the proportion of the variation of the y's predicted by the regression line, and 1 minus r squared is the proportion of the variation of the y's that's left in the scatter around the line. So how many people have learned that before? Have you heard about that? Usually it might be called the coefficient of determination. Is that how you learned it? Yeah. So, well, this is going to feature, this r squared is r squared, this correlation coefficient squared is featured in all regression analysis. It's going to come up a huge amount in this course, and it's a, so I just want to give you a little preview right now. It's featured in all regression analysis. All right. And we're going to be doing a lot of regression analysis. Now, you can think of r squared as a measure of the signal. There's a signal here, there's a model, and there's noise. So you can think of r squared as your model or your signal. And then the noise is like 1 minus r squared. That's the proportion of the variation of the y's that's left in the scatter around here. 1 minus this is the noise. And together, they make up the whole spread of the y's. But obviously, it's a tautology. We can say together they are 1 or 100%. It's going to be true of everything. And what we're going to apply this to is the variability of the y's here. So this right here, this statement follows directly from here. See this formula? All right, so let's look at that formula. This right here follows directly from that formula, because if you square both sides of that formula, right here, if you square both sides, what do you get? You get ST errors squared equals, we'll square that, that's 1 minus r, 1 minus, we'll keep it little r, but it's the same as, why don't I just call it big R? In this, it's the same when you have 1x. Okay, so 1 minus r, and then you square this, and you get the standard deviation of the y squared. So this is like the variability. If the standard deviation squared is the variance, so that's like the variance of our errors equals 1 minus r squared times, that's the variance of our y, or the total variance. So this is just saying that 1 minus r squared is the proportion of the total variability of your y values that's in the errors. And, and so if we do this, you'll see what I'm talking about. Just multiply this whole thing by the variance. This is true of everything. We're talking about the variance now. So you have r squared times the variance of the y's plus 1 minus r squared times the variance of the y's is equal to the total variance of the y's. And this is basically, you're breaking this variability of the y's into two parts. I don't want to spend too much time on it. It's already been 10 minutes. But basically, look, you get different scores on the final. That's your variability of the y's. You all didn't score average. If you all scored had the same final exam score, there'd be nothing to predict. So there's this variability I want to explain. I want to predict who's going to do better, who's going to do worse. So that's the spread of the y's. That's your total variability in what you're trying to predict. And you're trying to do it building a model using x. And in this case, we're building a line, a regression line, to make a prediction given an x of y. And this is our model right here. So the idea is you split up all your variability of the y-scores, how many points you got above and below the average. We want to explain that. And you split it into two parts. One is due to this model. This model will explain, will be the part that we can explain, we can predict. And the part we can't explain is all these errors. And so basically, you break up your variability of all your y's, whatever you're trying to predict, into two parts. And this part, r squared, this is this proportion of it. This is just strength of your model. This is the part your model's predicting. And this part is the part your model's not predicting. This is just the noise. So this is the strength of the errors. Okay? And this, breaking it up into two parts like this, partitioning your variance into two parts, your signal and your noise, is what's called analysis of variance. So this is the structure of, this is what's called analysis. Have you ever heard that term? Probably analysis of variance. In some contexts, people call it ANOVA. But basically, it's just a way to split up. It's a way to tease out the signal from the noise and then look at the ratio of your signal to your noise. So that's what a huge amount of the course is going to be about. So it's sort of, we're going to start doing this in simple regression in chapter 11. Okay, but first we have to think about, we haven't done in Stat 100, did you realize that we never did any inference on regression at all? Like you did inference, you tried to estimate, we learned how to estimate the population mean from a sample mean. We built, standard errors, confidence intervals, did hypothesis tests for the mean, for the percent, for the sum, for the difference of two means. We did t-tests and we did all that. But remember you just learned correlation, just descriptive on bivariate statistics, the relationship between x and y. All we did was descriptive statistics. We never said, did any kind of inference at all. We didn't build any standard errors. We didn't do any hypothesis tests. We didn't do any of that. So that's what we got to learn now. And that's what a huge amount of the course is going to be using these linear models to make predictions and do hypothesis tests. And so let's kind of fasten our seatbelt and go into this because I don't know, the beginning of it is kind of, the way it's usually taught is bothersome to me. I'll see if I can make it more intuitive. Okay, so far we've only used this regression descriptively, right? That's all we've done. Now what are we going to do? We want to use regression to make inferences about a wider population from what's known from our sample. That's what we want to do. All right? And so, and we want to build standard errors just like we did with around estimates of the mean. We want to build confidence intervals. We want to do hypothesis tests, everything. But before we do this, we have these four crucial assumptions that we have to talk about. That so their linearity, independence, equal variability, sometimes called homoscedasticity. Homo meaning same, scedasticity meaning spread, and normality of those errors. These errors, not in our sample, but in our entire population. We don't see that population, we just see our sample. But in order to do the methods that we're going to look at today, we have to make those assumptions. Now, why do we make those assumptions? Why? What happens when they're violated? Which assumption does what? Is what I'm going to try to give you a gut level, just to so that you'll remember why these matter. I mean, I'm sure if you're in other higher level statistics classes, you always hear, well, the assumption we're making is that the errors are IID normal 0 sigma squared. And that just means just this: identically distributed, independent, identically distributed with equal variability, normal with mean 0, that doesn't really matter. You can always adjust that, but the same sigma squared is the same variance. Okay, so that's what you hear all the time, but what does it all mean? So let's just go through it and try to logically figure it out. So, also, I think at this point, just because we're talking about making inference to a wider population, we're going to get really confused if we use the same equations, the same terminology for our sample stats and our population parameters. So it's a good time now to just make sure we're clear that whenever we're talking about the population, and we don't see the population. If we did, we wouldn't even be doing this. If we had the population, we wouldn't be taking a sample to infer anything about it. We'd be done, right? So this is unknown population out there. It's sort of, and we have this idea, this model of what it looks like. And we're going to start with a very, very simple linear model, just one x predicting one y. And this notation, you see, these betas are what we're estimating. They're population parameters. So here's the regression equation that we've been looking at so far. This is from our sample, let's say. Let's say this was our sample. And then this, well, the beta, both of these, when you have the 0 here, these are the intercepts. So that's the y-intercept. So that's put first because, and it's called 0, it has no x associated with it, so it's beta sub 0. Or if for our sample regression, we just use these Roman letters, B0, beta, B naught, or beta to predict beta naught. That's your y-intercept. And that's put first because then you're going to have a bunch of x's that follow. We only have one now, but we're going to, like we're predicting finals from our exams. But don't you want to have more information? Let's say we want to also predict it, use the homework. Let's say we also want to use your gender, your years. We're going to build these models, right? And so we're going to have lots of characteristics that are going to be able to predict some y value. And since we're just going to start with one of them, the first one is a slope for x, and I should put an x1. And so there, that's what it looks like. Then we'll have beta 2, the slope for x2, etc. So this is your slope in the population, and that is in the sample you see. And here's where the errors are normally, just this little thing means distributed. This is an assumption of the model, and they're normally distributed. Oops, I forgot to put independent. That's hugely important. Independent and normally distributed with the same sigma, the same standard deviation, the same spread. That's homoscedasticity, the same sigma to predict across all the x's, across the whole, all right? Now, all right, and then another important thing is we have to put a hat on our predicted values. Because this isn't your usual equation. This isn't all y's. This is our predicted y. Follows this. All right, and we put a little hat to indicate it's a prediction. So now let's go back. I'd like to use the same example. We did this example last time. We got the regression equation, if you recall, and but now what we're going to do is say, let's change the situation and pretend that the stat 100 students that we looked at last time we're actually a random sample from a much larger class. So basically, we're taking 100. Our sample size n is 100. It's going to figure in this n, because the bigger the sample, the more accurate our prediction will be about the whole population. So that's our sample size. It's from the previous example, a random sample from a much larger class of Stat 100 students. Let's say 2,000. And let's say we didn't have data on all 2,000, right? We could even say from the whole U of I, but it doesn't make sense because they didn't all take the same exams. But we did have 2,000 in Stat 100 and pretend it was a random sample, okay? And now we want to use this, let's say these 5 summary statistics, we can calculate because we have the 100 data points. We have the 100 people, each with their exam average and their final. We have those 100 points, and we can calculate the sample average for the exams and the final and the sample standard deviation and the correlation coefficient. So let's say we're given all, we've done that, right? Now, how are we going to, and then from this we can come up the same way we did before with the regression equation, right? But what we want to know is how we can use that slope we get here in our regression equation, or use this correlation coefficient to estimate what the correlation in our entire population. All right, so we'll set up a probability model, and imagine this, like a box model. We'll do this like we always do. This probability model, we'll randomly draw from it. So this is our box model, and it's going to be always, the probability model is, the box model is the entire population, and we're randomly drawing from it. So the whole population. So let's just draw, this is the whole, all 2,000 students, points. And the whole population always is this. Imagine this is the box model, right? But imagine not a box. I think it's easier for you to conceptualize the real scatter plot. Okay, so there's this real scatter plot. We don't see it, but here's the exams, and here's the final scores of the entire population, the whole population. Okay, so this is the population here, and we have 2,000 points in here. I'm not going to draw all 2,000 of them, but we don't know what it looks like, but now where do our assumptions come in? Okay, first of all, we don't see this, right? We don't see this. We're assuming it's linear in here, meaning that, can you see that there's a trend here? It's a linear, we can best fit this with a line, as opposed to, what if they look like this? Something like that, like a parabola or something. You know, we'd best fit it not with a line, with something else. So we want to assume it's linear just because, I mean, we could fit a line here. There's nothing stopping us. We'd get a slope of 0. We'd say there's no correlation, but that's a stupid model if we have a pattern like this, because we can do a lot better and we could fit a curve to it, or we could do some transformation of the data to make it linear. So we are, and that's to come. We're going to examine lots of curvilinear plots and later on. So basically, does the plot look like it might well fit with a straight line plus scatter? If not, if the apparent dependence shows a lot of curvature, we're going to use some other sort of fit besides a linear, besides this line. And that we will discuss later in detail. So let's just say if the plot looks linear, then we can go ahead and find the slope and find the intercept the same exact way we did in the previous chapter. We're just going to do that same thing again. But we don't see this, so how do I know? What am I looking at? Well, we're not looking at this. How can we determine whether we should fit a line? Well, what we are going to do, remember, is we do see one sample. And the idea, so we've randomly drawn out of this box. So we took these little points. You know, we randomly draw, and what do you think? In this case, it's n equals 100 points. Randomly draw n equals 100 points. Now, it's without replacement, and sometimes, if I wanted to be, we talked about in Stat 100 how sometimes you have to use the correction factor. But let's not worry about that now, okay? When you have without replacement, this 100 is a very small number compared to this 2,000. So let's just assume we don't have to worry about that. But I want you to be aware that we're doing without replacement. What do you mean? We're not like taking a student out and putting it back in. And we don't want to get the same student twice. We have 100 separate people here. All right, so we're randomly drawing these 100, and we get a sample scatter plot. And that's where we get these statistics from. And it's shown on the next page. So we can look at it. So here it is. It's the same plot that before we pretended was the whole class. And here is our scatter plot. So here we have the exams, and this is the sample scatter plot. This is all we see. And here we have the final. All right, now we look at this, and we say, does that show much curvature? It doesn't. It looks like a line does really well. So we say, okay, that assumption passes. The linear, that's where this comes in. Do we really even want to use a linear model at all? Okay, do we want to use this? Do we want to fit a regression line? And it looks to me like it makes sense. If you saw something that had a lot of curvature, I would say that we could do better. It's not like you can compute a line, but it doesn't make sense. Why not try to fit it better? But this one looks like a line's our best, so that's assumption 1. So let's go here and say, okay, assumption 1, linearity. Now, does our sample plot look like it might well fit with this straight line? We really want to know if this does, but we can't see it. These assumptions are all about the population, right? If not, okay, so now linear, so that's our assumption 1. So we ask, does our scatter plot look linear? And we decided yes. Okay? So we decided, yep, it does. Now, if it does, then we should go ahead and get our sample regression equation. And it's exactly like we did before, so maybe we don't have to waste time with it, but I'll just put in the notation. We're trying to get this right here. We're trying to solve for these, the beta naught and the beta 1, and this is the one, the slope is really of interest. People don't really care very much about that intercept. Okay? And so that's what we want to do. And last time, we saw that we got this. Let's look and see what we got, because it's going to be the same exact thing. No point in going over it again. There's exactly the same thing. So we said R times SDY over SDS is on page 29, and we took the ratio of Y is always what you're trying to predict. This is the same plot here. And so we said 10.3 over 9.2, and we got that. So we plugged that in here. Notice we've changed the order. We're no longer in the, we're just, in statistics, the convention always is to put the intercept first, and then you're going to follow by your slopes. So far, we've got this. And then to get the intercept, we said, okay, this equation's true of every point on the line. We didn't have this yet. So we might as well we know one point, the point of averages. So the final, 73.6, we know that point, 73.6, and 83 is on the line. So then we just solved, and we got 18. That's what we did here. All right, now that we have that, let's just let's put it in here. Okay, so just be careful. What's the 18? We rounded to 18 is beta naught, plus we got 0.67 for beta 1, and that's times x, which is our exams. All right, so that's where we're at, sorry. So far it looks good. That was linearity. Now we have 3 more assumptions to go, and where do they fit in, and how, what we're trying to do is use this slope here in our sample to estimate this slope that we don't know. So the slope here, or the correlation coefficient that we don't know. The slope here is we don't know beta 1. We're going to estimate it from B1, and we're going to say we just don't know that. We don't know the equation for this line. That's what we're trying to get at. Questions so far? All right. So we're estimating it as that, but remember, this is the whole point of inference. Our best estimate is 0.67. This is B1, it's going to estimate beta 1. That's our best estimate. So what are we doing now? Remember, each time you take a different 100 points out of here, you're going to get a different sample scatter plot. All of these are going to be different, right? You're going to get a different slope. You'll get a different equation. It's going to not be exactly this. It's going to vary just by the luck of the draw. And what we want to do is 2 things. We want to describe the typical variability. That's called the sampling error or the standard error of the slope. That's number 1. We want to do that. And then number 2, we want to think about what the distribution of the sample slope is. Does it, if we did that over and over and over again, would all the slopes follow a normal curve centered at the true value here? What would the distribution of, let's say each one of you took a sample. I gave you these 2,000 people. We could simulate it. We should do this as a homework problem. We do it as a homework problem in R. We could do it for us too. So each one of you, you take it randomly. We could give you all the numbers. You randomly take a sample of 100. You're all going to get different slopes. And then we could look at the distribution of those slopes. What would it look like? Would it look like the normal curve? Would it look like a T-curve? We have to think about what we know, and this is all the stuff we already know, the central limit theorem. This is all going to be exactly like what we did in Stat 100. We're going to apply those same principles. The bigger our sample, if we do 200 students, we're going to get a more accurate. We're going to get less error. Imagine if you only had a sample of 3. You picked out 3. You could pick out anything. You could pick out this, and this, and you could just have a really weird, you could have like any kind, you're going to have a tremendous variability with just 3 points in what your slope's going to look like, right? So the bigger your sample size, the more accurate your estimate, that we know that. And think about it, also, the less spread around here. Imagine if there was a perfect correlation. There was no spread. Well, then we'd get the same slope every single time, even if we had 3 points. There'd be 3 points on that line. There'd be no variability. So that's the structure. That's how we're going, like we always do. It's going to be some measure of standard error over square root of sample size, over the square root of n, right? SD over square root of n was what we did for all of our standard errors of estimates for means and percents. So we're just going, and we're going to do something very similar. That's where we're headed. Okay, so turn the page here. Now, so our sample slope, just like we said, is the best estimate of the population slope. Just to get this, not getting confused, sample slope is the B, and the population, our model out there is this Greek letter. Okay, But of course, it won't be exact, since each time we take a random sample, we're going to get a different set of points. So our sample slope will vary. By give or take what amount? That's called the standard error of the slope. Think of it as the sampling error of the slope. There's a true population slope, we just don't know it, and our sample is what's varying. We have error in our sample, and we want to quantify that error. So how much the sample slope typically varies is called this standard error of the slope, and it follows its own square root law. Remember, error scales as the square root of n. The bigger your sample size, you don't divide, the smaller your error, but you don't divide by n. You divide by the square root of n. So that's the square root law that we all know figures right in there. And you should all, that should be easy to remember, because we've studied this, so we've seen this over and over and over again, that the error scales. And the bigger your sample size, you know you're going to get more accuracy, right? You know you do. I mean, it's going to be, don't you have a better, if you have a bigger sample size, you're going to have a better estimate. So your error is going to go down, the bigger your sample size is. Now, okay, so this is just the standard error. Later we're going to do something called the standard error plus if we have small samples. Right now we're just going to do it for big samples, all right? Now this formula makes sense because the standard error of the slope comes from two sources, from the sample size, but it also comes from the random errors of y around the prediction line, just as we said back here. If this numerator, the standard deviation of the errors, is how spread out these errors are around this line. If you have a tremendous amount of error, well, then you're going to have a lot of variability in your sample slope. And if you have no error, you're going to get exactly this. You'll have no error. If all in your population, the standard deviation of the errors is 0, then your sampling variation, your standard error is 0. You're going to get the same slope every time. So that's what's in the numerator. So this looks fine, except how do you explain this SDX? Why is that there? You probably think, oh, that makes complete sense. Why are we putting this in? Well, I think you can see it a little better maybe if you think about, we're talking about a slope. So we're in the units of the slope. We're not in standard unit. We're in the units of the slope. We're saying this is the slope. We have, give or take, how many final points per exam point. For one exam point, how much does your final change? So it's final points per each exam point, right? So remember, I think maybe if I expand this out, remember this formula? It's the square root, SDRs is the square root of 1 minus r squared. And here we have the square root of n, but it's the square root of 1 minus r squared times SDY. So if we didn't put that in, this is what it would look like. And that doesn't make sense for a slope, because the variability would just be described in terms of y, right? If we didn't put that in. And slope is change in y per unit of x. So SDY over SDX, that part is because of we're talking about a slope. Okay? Does this make sense? As a way to remember it? Now don't get frightened. I want you to understand it, and eventually you are going to remember it, but it's kind of early still, and we're doing a lot of stuff before exam 1, so I am also going to give this to you on the first exam, just so that you can relax. But I really want you to, later on I might not, okay, but for the first exam, so it will be given on first exam. Now I'm not sure which form I'll give it in. I might just give it in that form. Okay, but you're going to get that too. So far you got those two formulas. Those I think, are going to be the only ones. All right, so we've got that done. Now, back to our assumptions. And you're going to see these assumptions over and over and over again. In every stats course you take, you're going to check your assumptions. I want you to know why or what difference it makes, because they're always going to be somewhat violated. You're not going to have perfect linearity. There might be some curvature. You're not going to have perfect variability or route of errors. And then you're going to have a lot of violations. So, like, let's understand how they matter. Do they matter? Okay. So why do we need these? We need assumptions 2 and 3 to use this, to derive it. If you want to derive it, and if anybody's interested, I can provide that. It's not that hard. But to use this standard error, you need assumptions 2 and 3. Why? Okay, so assumption 2 is independence of the errors. So the errors in the underlying regression model must be, so in the population, they must be mutually independent. What does that even mean? It means that we don't want to see any groupings. So what we're going to do, what you do typically do, and probably those in higher level stats classes know this, you always examine your residual plots for these, do these assumptions hold or not. So first of all, what does this even mean? Why does it matter? Independence. We want to see whether in the population the errors are independent, but we only see a sample, right? We see the scatter plot. Now, for linearity, it's easy pretty much to just look at the sample scatter plot, but it's actually, to examine these other assumptions, it's easier to look at what's called a residual plot. Super easy. It's basically just straightening this out so that we can see better, making it horizontal. So instead of having the y, this is y and x, we have the x here, but instead of y, we're just plotting the distances of the errors. So if a point's exactly on the line, it has 0 error right there. This point looks like you can see the measure of the error. Instead of saying, oh, that distance, it's easier to see here. Looks like it's about 15. So you can see them, and this is, to check the assumptions, you can look at either one. But it's usually easier to look at this, to spot assumption violations looking at this. So this is not y anymore. You know what it is? What would it be? It would be our actual y values, like the actual y values this is the actual final that this person got, minus what was predicted, that distance. This would be the actual, whoa, this person did terrible. Predicted to do much better, but actually did terrible. So you can see that person way down here, and you see how it's easier to spot, like which one is a bigger, like it's hard. Did this person or this person have a bigger error? But when you do it this way, you see they're pretty even, but this one looks a tad bigger, a tad worse, lower from the regression line. So what this is your y values, your actual y values, that's just little y, minus your predicted. And remember how we say that? That's the hat. That's your error. Another word for that is residuals or errors. That's errors and residuals are the same thing. So this is these are the residuals. I'll just call them the errors. And this is an error plot. Okay? That's all that is. So now I look at this, and if these little points were dependent, I want them to be independent. Why? Because if they were dependent, what would that even mean? In this example, let me give you an example of how they might be dependent. So here I'll just put this, I'll draw it up here. If you saw, this looks good. You see no pattern, no groupings. No groupings is good. How does that relate to whether they're independent or dependent? Okay, so here, remember what these are. These are exams, and these are the finals. And then this is no error. Now let's say they didn't look like this. Let's say like people some people, like a whole bunch of people did terrible on the exams, but they happened to, let's say they just we're all up here. So this is a whole group of people. We have 100 points. Let's say maybe there's 20 of them there. All right? And then let's say there's maybe 20 points down here and another 20 that are pretty close, like gathered there, and maybe we have another group here. I'm just making this up. 1, 2, 3, 4. And we'll do 5 of them. So let's say there's like 5 groups of 20. And this, how would this even happen? Let's say there were 5 sections. And let's say that everybody in this section had a lousy TA, and then he pretty much gave him the final before because he wanted to not get fired or something, things like that. Or didn't give him the final, but gave him practice finals that were almost identical. So maybe they were doing terrible because he was teaching terrible, and then, something like that. And then maybe here, this TA wasn't doing great, a little better on the exams, but maybe got sick or something and didn't teach in the last 2 weeks of the course. Or, what I'm saying is, why would this could happen? Like why does it matter? Because we said we had 100 points, but we really have basically 5. We don't have anywhere near 100 because they're pretty much all correlated. If you know one of these people scores, you know the others. I mean, with identical twins and things like height and weight, if you had all identical twins, you'd have half your, because if you know one, you're pretty close to the other. So the idea is we don't have as big a sample size. And that means that we can't use this formula. The N is wrong, okay? So this matters because if the points aren't independent, then in effect we don't have as big as N as we thought. We have way more error. We can't be nearly as sure of what's going on. Okay? So that's the idea. So check. So what you need to do is, in order to use this formula, you'd have to adjust your N if you see something like this. So you check that the residual plot shows no grouping like that. This is an extreme example. And if it does, you're going to have to figure out how to adjust your sample size. All right. Now, how about the equal variability? Equivariance, this is also known as you're going to see this as homoscedasticity. I don't have room to write it down, but that's what people call it. As opposed to heteroscedasticity, like homosexual is same-sex relationships, and heterosexual is different sex. So we want homoscedasticity. We want same variability. So let's first check the residual plot. What I mean is the variability across the different values of the x's. We want to have the same spread. Now you might say, that doesn't look like the same spread here, but that's just because there's so few points. Here we have lots of points. If we had lots of points here, we might have the same spread. What would it would look like would be like real spread out here. They'd be much bigger. Or if you look here, it'd have a much bigger spread. They're not the same across. This looks good. So we want to check, and we'll think about, well, first of all, why does that matter? This is needed because how much the scatter in the population, we're talking about in the population, affects the slope. Think of it. Depends where along x it occurs. Can you think about it? Changing y, if y has some error here, like if you get different y values, just by the luck of the draw, different, in the middle, it's not going to affect the tilt of your slope as much as if you get them out at the ends. Like if in the population there's a wide variation at either end, far away from the mean, well, just by the luck of the draw, you can get points way up here, and it's going to tilt things more. Whereas if you get them right in the middle, it's not going to affect it as much. So again, we are using one standard deviation, right? So we can't, to use this, if the situation has, we're going to have a lot more variability. I mean, this is okay if we assume homoscedasticity. But if we have a lot of variability at the ends, that's going to be really bad. That means we don't have this small an error. We have much more error. So check that the residual plot, this is also, we can use this formula. So this is check that residual plot doesn't, you know what you often see, the biggest violation? I'll just give you the typical one. You often see something like this. I'll just say, like, let's say, probably not in this case, but at all. So it's not a good example. You might, actually in this case, you might see like a lot of variability here, but not so much here. Like people do really well, usually do really well, but people who really bomb the first one, they have a lot of variability. So that's a fan-shaped pattern, right? And that's going to be bad to, we can't use this formula if it's like this. We have to do another adjustment, which we'll talk about how we'll take care of that later on. But check that the residual plot doesn't have a fan-shaped, or you could have the fan the other way, doesn't have a fan-like pattern. All right. Now, if this is all, after you look at your residual plots, and I'll tell you, this is the most boring thing you can do, is looking at these for me. Looking at their, unless you sort of understand the data and are interested in it, because honestly, this is really good, nice, this isn't violet, this is a really nice linear pattern. You're going to see things that, like, where do you draw the line? And when should you do these other, it's just always, so if you understand what's going on, it will help you a little bit. So now, attach the standard error. Okay, so now we got to get that standard error. Did we ever calculate it? No. So let's calculate it. We can, now this is good, we can calculate the standard error. So let's do it. So the standard error of our slope is what? That's what we're trying to do here. And it's the square root of 1 minus, now we're going to have to go back to the previous page for all these statistics. The only one we know here, I guess, is the square root of n is 100 here. But 1 minus, I remember it was 0.6 squared. And then we have the ratio of those standard deviations. We did that before. What was it? It was, we did it before, 10.3 over 9.2. That's why that's x. Remember, don't get those mixed up. That's the most common mistake. Okay, so we have 10.3 over 9.2. All right, and what I got was approximately 0.09. All right, so that's our standard error. And so right now, before we make any other assumptions and think about normality or the distribution of the sample slope, so we can compute confidence intervals, do significance tests, all we know right now is with this definition, we can say, okay, we predict the population slope to be that, and then we have this standard error, give or take 0.09, but we can't build we can't build a confidence interval. We can't, this is one standard error, and you're probably used to thinking, oh, one standard error. If the sample slope followed the normal curve, then we could say this is a 68% confidence interval. Well, it turns out it does follow the normal curve with a big enough sample size, and that's exactly what we're going to do. Exactly. So this will be a 68% confidence interval, one standard error, because 68% of the time on the normal, 68% of the area in the normal curve is between, this is the normal curve, is between z equals 1 and z equals -1. So this is 68%. So from here to here. So why can we use this normal curve? What are we even doing here? This is, in terms of, this is in terms of z-scores, in terms of actual data that we see, this is going to be our sample slopes. This will be all the different sample slopes. Like each one of you, remember, took a sample size of 100, got different points, computed slopes. You gave me we put them all together and we were going to plot them. Well, right here, you're most likely to get the true population slope. So that would be rho, the true population slope. Not rho, that's the true population correlation coefficient. This would be beta 1. That's, that's your true population slope. Beta 1 right here in the middle. This is a z-score, this is your slopes. But you're not all going to get, it's going to vary. Well, 68% of the time, you're going to be within, this 68% of this class, if we all did it, would be within 1 standard error of that true population. So you're going to say you're 68% sure that you're in that 68%. But how many of you? 32% of you aren't going to be that close just by the luck of the draw. You're all going to do everything just right, just like we just saw. But 32% of you just by the luck of the draw. That's what we mean to say you don't know where you are. You only see your sample. So you say, I'm 68% confident that I'm between 1, z-scores of 1 and negative 1. That's what a 68% confidence interval would be. So we can be 68% sure that our sample slope is within 1 standard error of the true population. Now what about a 95% confidence interval? Well, remember, where am I getting these 1s and negative 1s? If you think about the normal curve between z-scores of 1 and negative 1 is 68%. Right? It's a little bit less than, but we're rounding here. Now, let's say we wanted to be 95% sure. So we look at the middle area, because we know that 95% of us, if we all did this, are going to land between negative 2 and 2. So we look here, and we see 95%. All right, it's somewhere in here. We've been rounding to 2. But on your homework, you're going to have to be more exact and use 1.96 and actually use, I can show you the p-value calculator. So we'll look at that later. But this is where it's coming from. If we wanted to be 80% sure, what would we do? We'd look for the middle. That means we're 80% sure we're in this area, so we just have to find that's our what the z-score, this is called the critical value, corresponding to 80%. So we just go to 80%, and the critical value looks like we've been rounding to 1.3, but it's probably 1.28 or something, if we want it to be more exact. These are the critical values. So how do they figure in? We'll do the calculation, and then we'll talk about why we can use this distribution. So let's just first get the mechanics down, and then we'll talk about why I think that this follows the normal curve. Why does the sample slope? Let's first get it down, though. So we can be about 68% sure that our sample slope is within 1, assuming that it follows the normal curve and that these slopes, sample slopes, follow the normal curve. Okay? And 95%, because 95%, this is 68% of the area, 95% of the area is between negative 2 z-score and 2. This is where this is coming from. So you're 95% sure you're in this range. All right. Now, how do we build these confidence intervals? So in general, what do? Let's just take one of you. Imagine you have your sample. All you know is your sample. You don't know the true. You don't know if you're out here. You don't know where you are. So you know your sample In this case, let's just do, is there any of these questions? Let's do one of these. Should we do the 95%? Let's do this. Find the 95%. So the 95% confidence interval. Okay, so in general, you're going to get your sample slope. So let's say you got 0.67, all right? That's your sample slope. You want to be 95% confident that you want to attach some error bars, plus or minus some error bars, and you want to be 95% confident that you capture the true population percent. So what do you do, and why does this work? What you're going to do is do something called, right here, you're going to plus or minus, this is called the critical value. See, the confidence interval is of this form. The sample slope for the normal curve plus or minus the critical value for the corresponding confidence interval times the standard error. So here, the critical value for 95% z-score is, can I just round to 2? We know it's 1.96, but is it okay if I round to 2? Do you know what the 2 is, what the critical value is, z star for 95%? Do you understand that? Because between 2 and negative 2 is 95%. And we're going to multiply that by the standard error that we got. We're just following this, and I'll explain why it works. By the standard error, which is, we calculated it before, to be 0.09. So in other words, we take 0.67, and we subtract 2 standard errors, and that will give us our lower limit. So 2 times that is what? 0.18. We subtract it from that, and we get, that's our lower limit. And then our upper limit is we're going to add 0.2 times that. So our upper limit will be 0.85. And we say we're 95% sure the true population lies in that interval. So let's think about it and why we're doing this. Okay, so let's say you got 6.67 is your slope. Okay, this is your sample. You're 95% sure that you want to be 95% sure. So that means, what are you 95% sure? Well, if you know this is a sampling distribution, if you did this thousands and thousands and thousands of times and plot each time, each person taking 100 points out of the whole population, and you plotted your slopes, sure, there's going to be a hump around the true slope, but this is the distribution. And this is the distribution of the slopes. And you know that 95% of the time you're going to be in this range. Okay, you don't know where in this range, right? You could be right here and bingo, you nailed it. But let's say you're really, what are you confident of? So let's say you're at the very edge of this range, right here. Right at 2. Well, what are these? These are 2 standard errors in terms of slopes. 2 in terms of the z-score, but 2 standard errors in terms of slope. So you go over 2 standard errors, and you go way up here to 4 standard errors away, way out here. That's 0.85, let's say, if the true slope was, if you're 0.6, but then you go 2 down, and you just nailed it. 2 down. You just got the edge of it. That's if 0.67 was right here. Now, if it's anywhere closer, 95, you're going to be, then sure, you're going to, if you go, let's say it's here, go 2 standard errors here, and then you go up to -1 to 3. You easily capture the true population percentage. So that's the idea of this, and that's how it works. Now, we glossed over why I can use this normal, how we know it's distributed like this, right? So the key is that is the central limit theorem. It's a perfect case of the central limit theorem, because really what's happening is the errors in these slopes come from n random draws, independent draws, summing up those of independent errors. And the sum of n random draws, as long as n's big enough, no matter what I'm saying is, normality has not kicked in yet. You do not have to have normally distributed errors. What does that even mean, normally distributed errors? Normally distributed errors means that within each little vertical strip in the true population, so you have this true population, right? And we said it would look like this. We don't see it, we don't know it. We have this regression line. Da, da, da. What's normally distributed errors mean? It means, here's your x and here's your y. It means that if you take any vertical strip, I don't care where, that inside this strip, there's going to be like a little normal curve, meaning that there's going to be more points clustered closer to your regression line, and then there's not going to be weird out, it's not going to be skewed. It's going to be normal. Now that doesn't matter if you have a big sample size, just like it doesn't matter when you're sampling. The central limit theorem says that no matter how weird, how skewed or weird or abnormal, you can have the weirdest distribution in the world. It's the most beautiful theorem. Breathtakingly beautiful. It doesn't matter how crazily skewed it is. If you have enough draws from that, the sampling distribution of the sum and the average of those draws will be normal as long as your sample size is bigger. The more wildly skewed it is, like the way income distribution is, the longer it will take. But it will happen as long as you have a big enough sample size. So even if the population's huge, infinite, as long as let's not get too complicated, but yeah, that's what the central limit theorem says. So we know, and generally speaking, with this 100, usually people draw the cutoff about 30. So so that's what we're doing. You know what to do here. We still haven't brought in our last assumption of normality. So where does that come in? So I think you understand all this. We don't have to do, which of the following statements is true? So we're 95% confident that the true population that we drew from, the true population slope from the 2,000 students, falls in this limit. We cannot apply it to, lots of people think, oh, since that means that there's that this same interval, we can be 95% confident that the slope of the regression equation predicting final scores from exam scores for the females will be within there. No, you can't be. You can't apply it to a more restricted population. You can't apply it to just the A students. That wouldn't even make sense. Think about it that way. You can't. You can only apply it to the population that you randomly drew from, not a narrow, more restricted or a wider one. We couldn't apply it to all U of I students. We couldn't apply it to this class, right? We can't apply that to Stat 200. It's only this one, all right? So let's just write that down. Just be sure of what you're doing here. The confidence intervals, when we do this, we do the calculation. Now, what does it mean? Can only be applied to the population the sample was randomly drawn from, not to a wider one or a narrow one. And you should understand randomly drawn from. Okay. And that should be apparent here. What we're saying is that if you drew from that population, that same population, this would be the spread. Not a narrower population, not a different population. That population you're randomly drawing from that has this true population slope. All right, I think we're good now. Whoa. All right, we have 10 minutes left. I think what I want to do is just show you the t-distribution. So why don't we, here is an example where I only have a sample of 25. And does drinking, everybody wants to know, is there a correlation between drinking and GPA? You assume it's negative, but is it really? So let's say we randomly drew 25 students. We know what the probability from all of U of I. So there's a scatter plot here that has all of U of I students in it. It has a zillion students. We don't know what it looks like, and we're trying to predict your GPA from the number of drinks per week. This is a question that's on your survey. So we're going to be looking at this question. You think it might be negative? Is it? Let's see. So you randomly, now we have a small sample, okay? And in our sample, we get these statistics, okay? And this is what we get, all right? So you can get a slope from this, calculate the sample slope. So the sample slope is going to be what? R, negative 0.2, times the ratio of the sample SDs. Oh, sorry, sample SDs. Now we're predicting GPA from drinks, so this is Y, and this is X. So we have 0.5 over 5. So we get negative 0.02. Now it's a very small slope, but is it significant? Calculate it, no. Let's not do this. Let's do it with the T. This is asking you to do it with the Z. No, this is a small sample, so the central limit theorem might not have kicked in yet. We have to be careful, so we have to do something different, and let's read about what we have to do. So, what do? And this is true. We've seen this before if you've ever thought about T distributions, so I'm just going to go over it quickly. Remember what we need to do. Our standard, we have more uncertainty. So we're going to do two things. Since our sample size is small, you can use T with large N. Lots of people do. It's just not necessary. But most software programs do it anyway. So this is what they're doing. We don't have to, but they do. So your sample size is small. And your errors around the regression line, here's the normality. You can't use this unless you've got those little normal strips, right? People do it all, but that's really the assumption. That's where normality comes in. Only. That's where it comes in. That when they say normal errors, it's so in a small sample size you can use T before the central limit theorem kicks in. And the standard deviations of the errors are unknown. Well, they're always unknown. And here's a nice acronym to use. SNUT, small, normally distributed, unknown SDs, use T. Now, two adjustments. We use SE plus. Now, you could have done that with Z. There's no reason not to. We just didn't bother doing that. Because once the sample size is large enough to use the normal distribution, this is such a tiny little insignificant difference. So what do? This is exactly like, okay, instead of doing, how are we going to adjust this? We already know the standard error for the slope without the plus there, just the one we've been using, is what? The square root of 1 minus r squared times the SDYs over the square root of n times SDX. Well, remember how you make an adjustment with n? Like you subtract 1 when you're estimating the mean? Because 1 point, if you just do 1 point, that's the mean. To get variability around the mean, you at least have to have 2. Well, same, now we have a line. If you have 2 points, you're always going to get no variability. You need at least 3 to reasonably estimate the variability. That's what I say here. So we call it the degrees of freedom are n minus 2. All right, so when you have a small sample size, this makes your standard error of the slope quite a bit bigger. Next adjustment we make are these T curves. Now the important thing about the T is it's a whole family of curves. There's not just one. There's one for every sample size. So here's a picture. What I want you to see is right here, the one that's skinniest in the tails and the tallest. It's the most compressed. Think of it as squeezing in the most, gives you the most accuracy, is our normal curve. As your sample size gets bigger, it gets very close to that. So what are all these here? Oh, so sorry again. So that's our normal curve. Now, k equals 1 means k degrees of freedom. So you have a sample size of 3. So this is what the curve, the sampling distribution, looks like when you have only 3 points. You have a lot more error. You have more error here, adjusting it, and look how much more spread out it is. So if you want to do a 95% confidence interval, you're going to have to go way further out than if you use the normal curve. So with small samples, it's imperative that you do use this t-distribution. All right, now how do we get the critical values? So we'll just in 2 minutes left, let's do that. So we have this. First of all, let's do our standard error. What is our standard error for the slope? So that's our first, and we're just going to do the same thing. It's the square root of 1 minus r squared times the standard deviation of y, standard deviation of x, over the square root of not n, but n minus 2. And that's our degrees of freedom. 2 is n minus 2. So we get the square root of 1 minus, now you remember our slope was negative 0.2. So we're going to square that. And then we're going to have the square root of 23. 25 minus 2. And that's our degrees of freedom, not the square root, but the 23 is. And then we're going to do the ratio of our standard deviations. So I did all that, and I got this. That's bigger. You see, it's bigger by what factor? By a factor of square root of 20. If I multiply this by the square root of this square root of 23, if I multiply by the square root of 23 over the square root of 25 to make it smaller, that's how much smaller our regular standard error would be. Now, how does it compare to the one? Okay, now 95% confidence interval. How does that compare? So this is the last thing we're going to do. And the 95, it's the same thing. It's your sample slope, which case, what was our sample slope? It's negative 0.02. That was our slope. Then it's going to be plus and minus the critical value for t with 23 degrees of freedom. Degrees of freedom is equal to n minus 2. So we're going to have to look at that times our standard error plus for the slope. So we're going to get, we know this, that's right there. Let's put it in, 0.0204. So I just want to show you how to get this. All right. This, I didn't include a symmetrical t distribution, so use the one from Stat 100. We didn't build these confidence intervals. So this area right here, if you're using this, so sorry, gives you the area of one tail. So double this and you'll have the area of both tails. We want 95% confidence interval. So we're going to have to, this is the area of one tail, double it. So this would be the 95% confidence interval. This, if you double 0.5 in each, this would be a 99% confidence interval. This would be a 90% confidence interval. Now, for 23, you have to look at the right. I mean, if we had a sample size, degrees of freedom 1, we'd have a huge critical value. But we're all the way down at 23. It's getting close to our regular one with the normal curve of 2. It's 2.07. So that's what we're using. It's right here, 2.07. And this is what you get, and I'll just show you one, I'll do it and show you one thing, that this all goes down to negative, so it could be negative correlation in the whole population. You could have this negative effect, but check this out. It goes all the way up to a positive. So in other words, we can't conclude a significance test would reject the null that would not reject it. We easily be no correlation. I think there's no correlation on this campus between drinking and GPA, and this would show that. But we'll see what our data shows. So that's it, and I'm going to post the homework. I'm sorry we didn't get to do eye clickers, and we went over a little.